All right, let's do this. So good morning, welcome to the 2017 DevCon. I'm excited to, it's always rough going after the keynote because they're always awesome, but hopefully we'll have some fun here today as well. So for those of you who don't know me, my name is Ryan Brush. I've been with Cerner for quite some time now, and these days I kind of just view my role as sort of trying to make sense of really big, complicated, nasty data sets and create value from it. So the good news is that we have lots of data, and it's really rich, sophisticated data. I mean, in healthy intent alone, we have one of the most probably complete data sets that exists in healthcare. The not so good news is that it's really complicated, and it's quite hard to make sense of it. It's quite hard to quickly create new value out of these very large data sets. And even it's a challenge to ask even simple questions about this data as it changes. So if we look at something, say, oh, here's like a really simplified view of some healthy intent data, and okay, by the way, there's a problem here. And can you see it? And oh, it's different here. Can you see the problems that change? Can you tell the difference there? One of the things that we're going to do in this talk is we're going to take these very large data sets and we're going to track down what these problems are. So how do you even approach this, telling, hey, our data changed from here to here, do we know what it means? Well, we could just add monitoring to it, right, and to see, oh, let's see if it changed. The problem is that, of course, everything is always changing. Our data sets are constantly evolving. There's so many variables. How do we know what matters whether this change from this to this is important? So we want to talk about a set of tools that we can bring to bear to tackle these hugely complex problems that we're facing with data. And I want to combine a couple industries to approach this problem. So one that I think a lot of this audience is pretty familiar with is good software engineering practices. How can we apply these practices to data problems? And we're going to also bring in statistics. And I know you're nervous, but that's all right. We're going to work through this together. And if we look sort of at that intersection, the talk is titled Data Engineering, so I better say what it is. It's really the combination of software engineering and some statistics practices. Now, if you're like me and we started jumping into this, this was kind of my initial reaction. Oh, statistics? Great. What are we going to do here? So since a lot of this audience probably is more of a software engineering background than a statistical background, myself included, well, here, why don't you guys go ahead and read this and get you started here. I'll get and take a drink of water. Oh, sorry. Here, all right. You done? All right. So maybe we should take a different approach here when we look at our statistics. And really, I just think of it with a really simple definition, is that given a set of data, what can we tell about the process that created that data? And we do this all the time, right? I mean, given some sort of set of data in our systems, we need to understand how it was created, and that process could come from the clinical processes that originated data to all the transformations and the mappings and all the work that's done to land in that final data set. And so if you're curious, probability is just the opposite of this, right? And so given, once you know the process, what data will have produced. But this is what we do. I would argue that we do statistics all the time. So let's create some structure around this, where we can make sense of whether these differences are meaningful. And how can we reliably tell if these differences are meaningful? Now, my goal here isn't, this is a data engineering talk. This isn't like a primer on statistics. So I'm not going to go into a lot of depth in that space. And I don't think that necessarily we as software engineers need to really be hardcore statisticians. But what I think we do need is we need to have some sort of intuition about what statistics can accomplish, how we can apply it to the problems that we're faced. And so that way therefore we know when we're tackling some new problem area, what tools exist to tackle it. So how do we combine this data engineering, this combination of software engineering and statistics to it? Well, let's look at some ideas that we can draw from. So one is, let's draw from these software engineering ideas where we all have unit tests, right? And these unit tests, our approaches have evolved over time. When I first started writing unit tests, when many did, I did a very example-based unit test, like, oh, here's a very specific use case, and we're going to write something that handles just this one particular item. but over time, we want to generalize it to property-based, where we think about, hey, what are the important properties of our system? Let's make sure we get those properties. Examples change all the time in our system, but the properties should stay the same. So rather than testing, hey, these two numbers equal each other, we should write tests like, hey, addition is commutative. And we kind of enter what I call this robustness loop in software engineering. It's like we figure out what are the important properties of the system, and we automate the tests to do that. And then as we find new properties, we automate new tests. And software over time, while never perfect, is always trending towards a stronger and stronger state. And so this kind of leads to us is if we think about dealing with these huge complicated data sets and making sure that these data sets are solid and reliable and robust, is think about some of the properties that we have. And so, working in the healthy intent space, think what are some of the properties of these data sets that we're working with? Well, some of them might be simple, like if a data set's only appending new information, it should always grow over time. So that's a property that we can check for. Some particular data elements have their own properties, like temperatures would be basically roughly normally distributed. We might expect that we'd see a consistent number, about the same number of lab results per person over a period of time, and if there was like a huge jump in that or something, that could be a flag that something's mapped wrong or something is inconsistent. Or if we're producing some sort of outcome, some sort of score, we want these to be roughly stable over time. If they're jumping back and forth a lot, that can be a problem. So here's the properties, here's just some properties. And you think about almost anything that we can count in our system can be a property that we can track and manage. So how do we do this against data sets? Because data changes all the time. If my average risk score, for instance, in January is here, and my average risk score in February is there, is that good? Things change. Is that a problem? Is that enough of a jump that I should worry about it? And it gets more complicated because we don't really know beforehand and in general what the distribution of these things look like. I mean, the distribution of risk scores could be some sort of radical multimodal system. I mean, some data sets tend to be normally distributed, but we can't assume that in the general case. And do we know did something change in our data feed? Or did it break? Or did some new feed get mapped in? Or did something change in how we're mapping these data and transforming it through the system? So how do we tell this sort of things? How do we find this correctness? Well, the first thing we can do is we can get a little clue here. And that if we take these data sets, and you kind of think of these as the point in January and the point in February. I mean, these are just samples of this broader process. The average of these are the averages of this broader process. So if we just keep on taking new averages of this distribution over time, something kind of cool happens in that no matter what the distribution of data is, no matter what this crazy curve looks like, if we keep taking these samples of it, it's going to be normally distributed. And so this is like the most important, this should be like the key to our intuition that we want to build when applying statistics to large data sets, is that no matter what the distribution is, the sampling distribution is going to be normally distributed. And this kind of gives us a clue, right? Because if we want to tell if our data points from January and February, if they are sort of the same thing, if they come from the same process, then we can tell that, we can get an idea of that. It's like how likely it is that these things could come from from the same distribution. So let's jump into this a little bit. I have these data points over time. We're troubleshooting our system, and I might have this default belief where nothing broke, right? I think that my system was good in January. I hope that it's good in February. Can we prove it? And this is basically a way of saying January and February are just samples from this same distribution of data. And so if you come from a statistics background, you might call this the null hypothesis, right? But it's just really, I'm just going to assume that, hey, these things are the same. Let's look for evidence to see if things change enough that I need to be worried about how my data changed over time. So how can we go about that? And I'm going to look at how we can tackle this problem without even having a brute force approach, without even have to tap into statistics at all. And then we're going to go and we're actually going to solve this problem for a real case in which our scores changed over time and we need to troubleshoot what that root cause is. So let's look at our brute force approach. Well, the first thing is that our average there from that January timeframe, it's made up of many other data points. And I think we can get an idea of how likely it is other things could be made up of similar data points by just sort of taking random samples of it. So I might choose some random sample of that and compute the average there. I'll choose another random sample there, compute the average. And we can do this thousands of times. And when we do it, take this random sample, compute the average again and again, we'll see this distribution of data. So we're taking these samples of our history, and we're seeing how it's distributed across these new data sets. And then we can look at it and say, how likely is it that our February result, how often did something as extreme as the February result come up when we sampled the data again and again and again? So I'm not doing any necessarily statistical approach, I'm just doing this brute force mechanism of looking at our historical data, seeing what the average of that was, and then looking at our new data and seeing how likely would that have occurred if I just sort of resampled my historical data many, many thousands of times. And if it's very likely, then, well, it looks like it came from the same process where data is probably okay. If it's really unlikely, if it's further out, if it's unlikely that our samples would have hit that, then it indicates that we have a problem. It indicates that something changed in a way that maybe we should track down. Maybe we should worry about that. And you can actually write little pieces of code to simulate all this, and you'll actually see the normal curve emerge from out of this. But the nice thing is that we don't have to go through that process every time. We don't have to simulate all this data. How likely or how unlikely something is to occur is, I mean, statisticians will call that a p-value, but you can just kind of think of it as what's the chances of something changes this, assuming that our process hasn't broken. And we can apply hypothesis tests to this sort of thing. I'm not going to go deep into this. Again, we're kind of building this intuition of looking at our historical data and seeing how can we figure out whether it makes sense. We can measure the changes of the size. So this is one of these toolkits that we have when we want to look at these properties that we've wanted to solve historically. Now, the first one, kind of gray out there because that's simple arithmetic. We can track trends over time. But the other ones, I think, are really important. If our risk scores or some other product that we produce jumps in a big way, how do we detect that across all of these systems that we might be building? And so we kind of enter this again, this loop, this robustness loop that we saw in our software engineering practices, where we want to identify these properties. We want to define tests that handle them statistically, and we want to build that into our system and then iterate on that. And we can detect these sorts of problems that we couldn't otherwise detect and sort of think of ourselves as detectives as we explore and manipulate and see if we can figure out the nature of this data. So the question is this enough? Are we there yet? And I think that maybe we have some tools. Hopefully we have some intuition of how we can understand how our data changes over time and track and improve it. But I don't think we are there yet because I feel like we do this every time we want to implement these types of solutions, in that it feels like a craft rather than an engineering discipline, and that we're weaving things together in distinct ways every time we want to tackle this. So even though if we can have this intuition about how to understand and manipulate our data, it's very customized. And this goes back to kind of how we might think about software engineering practices. I mean, so today, you don't write your own garbage collector, right? And that's ridiculous. But we're always writing our own archiving logic for all of our code. We wouldn't come up with our own way to modularize our code. The system provides that. We wouldn't come up with our package and classes mechanism, but we're always coming up with different ways to organize our data versus using an off-the-shelf way to package it, organize, and structure it. And because all of these things are sort of custom built, because it's a craft in so many areas, we've had a hard time applying things like rigorous measurements of tracking changes over time or ability to tap into value and explore it. And so I think the next piece of data engineering, when we started with some of the statistical pieces, is building these sorts of data APIs where we can archive, we can explore, we can tap into it, and we get all these advantages. We don't have to write our own garbage collector because we can use an off-the-shelf archiving mechanism that's built on a common structure of data. Now, there's been missteps in this path down the industry is quickly evolving these large data spaces, but I think we're starting to see some more clarity here. In the big data space, everything seems to be converging as Hive. The metastore itself is this catalog of data. For those of you that don't work in the Hadoop space, I mean, Hive is SQL that can compile down to MapReduce, but well, the interesting part of Hive isn't that. It's that they've built a catalog of data, this sort of data dictionary that can be leveraged by a whole bunch of tools. And I want to stress that by having this catalog isn't an abstraction leak. We can have this data catalog, and the underlying implementation is independent of it. It can be stored in Avro or Parquet, whatever your favorite file format, CSVs or HBase, or even external databases can all live under one common data catalog. So think of the catalog as less of an abstraction leak, but really think of it as a contract. It contracts the shape of your data from the store to the user, and it's a logical contract in that the data can be stored in many different ways. And so this is sort of like a higher-level uniform API. And Michelle Brush has expanded on this. There's a link to her blog post below, and there'll be more content coming in this space. It kind of generalized this sort of pattern for the big data catalog into breaking things down into different contexts, so we can work with either streaming ways to flow through the system or with RESTful services depending on the access pattern, depending on the usage needs. In this talk, I'm very much focused on sort of our large data catalog access patterns, but this is definitely worth leading, and this is going to be a definitely growth area there. So we have these pieces. Now, if you remember earlier in the talk that I mentioned is when we looked at these data sets, there was something wrong with it. There's a problem in our data in that our risk scores jumped between January and February, and we don't know if that's a good thing. How do we detect that? How do we track it down? Well, I think that now, hopefully, we've introduced some pieces. We've introduced some ways that we can understand, hey, are the differences between these particular data sets significant over time? And we've introduced ways that we can catalog this data and tap into it in common ways so I can do this analysis without having to redo it custom by hand. So let's go ahead and see if we can make sense of this data problem that we're dealing with. And this is always the scariest part of the talk of switching between modes here. All right, well that went, all right. So here we're going to bring up an interactive notebook to explore some of our data sets. Now, if you're familiar with some of the stuff that we're doing for deep analysis or machine learning in the healthy intent space, this will look familiar. But really, this is a general tool, and this is just a notebook, an interactive session to explore data sets. Now, our problem is that we have data change between January and February, and we don't know if it's a good change or if it's a bad change, or how do we track it down. So let's track it down. The first thing that we're going to do is we're going to look at we're going to organize our data into a catalog. So in this case, just for this example, I created this database called large population record, and has all the elements from the population record here. I simplified a bit and only included the subset that we're interested in this example. So what we're going to do as we build this out is we're going to create these sort of simplified views of these tables. So one thing that I didn't mention is that to create these risk scores, we can do it in a variety of ways. Oftentimes in healthy intent, we'll go through where we follow this pattern. We have very large, complex data sets. We'll project it onto a simpler model, and then maybe project it onto multiple simpler models. We'll do some arithmetic on that simpler model, and then produce some sort of score at the end. So we see this pattern again and again. Very complex data projected onto simpler data, which we manipulate and produce some sort of outcome. What I'm doing in this example is that we're going to use SQL to do that simplified projection of complex data onto simpler data. In many cases, SQL may not be expressive enough, so we might have to write Java code or might have to write Synapse, which is probably the predominant way of doing that in healthy intent today. For this example, and I think there's a reasonable number of other examples, we can just use SQL. So we're going to build our risk score model here, and then we're going to run it and see if we can track down data issues. So all it is just SQL from this data, and I'll kind of go through these few things quickly since we started a few minutes late here. So the first thing is that, well, we just want to get some information about the person, and maybe our risk score model wants the age and whether they're deceased or not. So we can just write some simple SQL to get that, build a table of it. And the next one, we kind of follow the same pattern of we want to get, hey, when was the latest asthma condition reported for this, and the number of times for a bunch of different conditions. So this is just off-the-shelf SQL. The only thing that you see sort of unique here are these has concept functions. These are just user-defined functions to say, hey, does this condition code map this particular concept, which is sort of a collection of code values. And then we'll filter that down. So all we're doing is we're kind of taking the ingredients of our predictive model, of our risk score, and turning into a bunch of spreadsheets. So we'll jump into the results score here and expand that. And you can even interactively, one of the nice things about having everything on this data catalog is that you can interactively manipulate it and explore it. So if this didn't look right to me, maybe I can add a clause where, this is greater than 130, and I can, rerun that. This is why you don't live code. So yeah, probably didn't add that there. All right, and then we can continue down on that process. So we'll expand some of these other examples here. And then ultimately, we're going to run this spreadsheet that we produce that contains all of our elements that we put together, and we can produce a risk score. And so we end up with a big table that looks like this, where we have, and oftentimes these will be sparsely populated, but you can see the risk score, you can see the MAC glucose, a bunch of inputs for it. So similar pattern here. So let's figure out if there's something wrong with our data sets. Well, the first thing we'll do is, let's look at our risk score table. We'll calculate some basic statistics of it. So we'll get our average score, the standard deviation, the count. And so, okay, that looks fine. Now, since we have everything, this data catalog that we've been working with, let's look at an earlier version of it. So this test data I had was from 2010, so I'm going to jump back to an earlier version of it. And part of this managing data in catalogs is really about keeping good versions and good partitions of it. So I'll look at this older version of it and say, well, the average there is 98. So it changed a bit, right? I mean, from one point time to another, it changed a bit. But is this something that we need to worry about, or is this just sort of normal churn in the system? So let's go back to let's see if we can answer that question of whether our data change in here is something that we need to worry about. So what we'll do is we're going to actually run a hypothesis test between our different columns. So what we'll do here is just gather some basic information, is our average and the standard deviation of our current risk score, the average and standard deviation of the previous one, and then we'll just pass that into a simple off-the-shelf function that performs a t-test. And something interesting happens here in that the statistic, actually the p-value, the probability of them coming from the same distribution, it actually rounds way down to 0. So, and this is actually a problem that we'll see frequently when we're working with really large data sets, because when you have very, very large sample sizes, it's very, even small shifts in the commonality of this data set will show that, hey, it looks like there's a very low probability that these things could have come from the same distribution. So, but this kind of indicates, well, there's something wrong with this. These have changed. So maybe what we'll do, we'll take the next step, and building on this catalog of data, let's graph our risk scores. So we'll have the score from 1, and we'll look at the 2 separate ones. So as you can see, there's a commonality hump there, but our second one, our newer risk score, has this additional hump of data here. And I think this is kind of interesting to look at by itself, because you can see this isn't a normal distribution. Neither of these are. It's this sort of bimodal flow. So we can't assume it's normally distributed. But it certainly looks like it's different. It looks like our scores have changed. So let's get an idea of how much now the question is how much did they change? And do we need to worry about it? So the next step is that we want to measure the size of the effect. And this is kind of an arbitrary scale, but I'm going to just compute the effect size, again, using these off-the-shelf functions between the two. And then I can see, well, there's a bit of change between our risk score from one point in time to another. So we have a clue here, right? It looks like our scores have changed. It looks like they've changed in a way that isn't tiny. This might be something to worry about. But we don't know what caused it. And I think this leads into this next step of applying data engineering to help understand and help solve this problem. So I wrote this function here, and I think that we're going to start seeing these sort of things sort of emerge on top of our common catalog of data. And that all I'm doing is when our risk scores change, I want to understand, hey, what inputs change and how did they deal with it? So what this did is by looking at this table that we put together, this giant spreadsheet of data, I'm going to look at every single column, every single numeric column, and I'm going to compare, I'm going to do a test between what happened in January and what happened in February, and see what inputs changed in that, see if we can figure out what broke, what caused our risk scores to change significantly. So if I run this function, all I do is get all the columns, I compute a t-test between the two, and then produce a table that shows that. So if I run that, and then I basically sort by how big the effect size. And we can do this for like thousands of columns, for complex data transformations that have many, many inputs. We do this for many thousands of columns. And then by sorting it, I can see, So we knew our risk score changed, we already checked that. But the thing that bubbles to the top of the list for things that change the most is our glucose reading. So we've gone from, and notice that I didn't have to go manually select any specific rows or manually look at any specific people. I can look at what my data looked like in the past. I can look at what it looks like now. I can see I can get a pretty good clue of this. Our problem came from our change in this very specific thing. Now we can, on our data APIs, we can sort of drill down into it, and we'll just sort of plot a histogram that compares our max scores, our glucose, from our current data and our previous data. So, and these look like pretty different distributions, right? And this is just a normalized histogram where we have a peak here for one, and then the other has this long tail of how data is distributed differently. So this gives us a pretty good idea. I think the next thing that we want to do is in approaching our root cause is realizing that as part of like this sort of data engineering API, it's really important that we think of everything that we possibly can as a data set. Because if you think of everything as we can as a data set, that suddenly makes it available to this rich set of troubleshooting tools. So my suspicion, based on our glucose level being changed so significantly, is that something changed in the way it's mapped, or we brought in some different data. So so if we looked at the SQL that we used to generate this function in the first place, we'll say, hey, if it has, we basically check for this glucose level concept. Well, maybe something about this concept changed over time. So what I'm going to do next is we can take all those concepts, we put it on another table, we're going to join to that, and then we're going to see for every code value that represented this glucose level, what sort of data values do we see there. And so as we can see for these different glucose code values, we can see the averages are quite different. And this kind of gives us a pretty good idea of what changed over time. Is like we have different code values mapped into this. They have different distributions, and we can drill down and say, well, yeah, this looks like something got mapped in a different way. And at this point, I have to confess that is in fact the case, and I intentionally broke the mapping from one version to another, and then got down to this. But I kind of want to think about, what it would have taken to solve this sort of thing. First of all, historically, we'd have a hard time detecting it because data changes all the time, constantly churning. How do we know if it's significant? Well, we can use that test to see the significance, to see that effect size. Then once we know that our risk scores changed in an important way, then we can go through and we can just do a test on every single input between these two versions of the system and see, hey, what shifted in a big way and what didn't. And just by sorting it, the root cause, not the root cause, but a very good indicator of what happened in our system just sort of boils to the top. And I think this is important why we need to start thinking about sort of this combination of statistics and data engineering, bringing it together to solve the problem. So I'll go back to our slides a little bit. Now, historically, we've kind of broken things down into these two different ways of working with data, and that we might have systems that are expressive but difficult to use. That more sophisticated statistics is powerful but difficult to use. MapReduce is powerful but difficult to use. And then on the other hand, we have something that's easier. So SQL is more accessible, or Tableau or something like that. But we really want to be more like a spectrum in this, and where we have something that you might think of a data lake is there when we need it, or we can use a warehouse model. Machine learning is an expressive model but difficult, or reporting is much easier to access, is much more accessible. And ultimately, when it comes to thinking about this system, is like, let's start thinking not in terms of these different types of systems, but let's think in terms of, can we create a slider where I can use things, like an interactive notebook that I just demonstrate when I need to do ad hoc analysis of the system. But if I need sophisticated logic, I can plug that in when necessary. And by building these common catalogs and these common data sets, we can get there. And then perhaps somewhere in the middle, we can start building these libraries of what are the properties of our system? What are the things that we want to preserve? What do we want to make sense over time for this? And when working through this and combining these disciplines of software and data engineering, I think the most important thing that we want to keep in mind is put yourselves in the shoes of your user. Put yourselves in this, or better yet, even be your own user. In that interactive demo that I showed there when doing analysis inside that notebook and statistics, and the data models that we used there, I mean, really the population record expanded into where each entity is an item in the database, and everything's partitioned by time, and we can jump between versions and compare it. I mean, that wasn't something that's necessarily immediately obvious. How to organize, how to structure. There's very oftentimes the best solutions are very non-obvious. And the best way to do it is really to become a user of these systems and to start doing this exploratory type of analysis yourself and design your data APIs, design your data catalogs in a way that we can most leverage it for a lot of these use cases. And so I think everyone should sort of be playing this role, at least in some way. And really, this boils down to, because ultimately engineering is about people, and that every single step forward that we've made in any engineering discipline, and any software engineering discipline in particular, is about making things simpler for us people. We went from assembly languages to interpret languages to managed memory, from manual memory to managed memory, all to make things simpler for us to work with. And I think this is one thing that we need to better optimize for when working with very large, complex data sets. Optimize for the user. Optimize to understand the problem. Because of all these really complex data problems, I've never seen one that isn't solved once you kind of simplify it enough. And so we need to optimize for ways to make things simpler, make things more accessible, because once we understand it, we can usually solve it. And with that, I'm about out of time, but I will hang out up here if anyone has any questions afterwards. So thank you.